This lesson discusses symmetry, which goes with section 9.6. So if you would maybe pause the video, I have a few definitions here for line symmetry and rotational symmetry. I think it would be best if you paused it, wrote the definitions down, come back, and then I'll go through a couple of extra things regarding these words. So go ahead and pause now. Okay, for line symmetry, one way to summarize all of this, I'm going to write the word, fold over here. Let me try to write better here. Fold. So I think of just having a line, and then I can fold over the line. And if the left side equals the right side, or top to bottom, then it has line symmetry. Versus like turn or rotate. If you can spin it or turn it and it lands, it looks exactly the same as before you started moving it, it has rotation symmetry. Now, the item over here with 180. So even if something has more than 180 degree rotational symmetry, we would stop at that point. So what I mean by that, if I just assume this is a square. If I go to rotate it a quarter of a turn, it's going to look the same. And then I can rotate it one more quarter. It's going to look the same again and again. So if I describe it, I could go 90 degrees 4 different times. So when I go to describe it, I would start by saying, yeah, it has 90 degree rotational symmetry. And so if I go 90 more, I have accumulated up to 180 degree symmetry. So I don't want to keep going and say 270. Because 270 is really 90 the other way. So we really just stop when we get up to 180, even if there are more rotations we could go. It's sort of implied that that is picked up the other way. So we'll look more at that when we get to those types of examples. So let's move on to a few examples on line symmetry. So one way you could do this is to go ahead and draw as many lines as you can, or you could just you might be able to look at the shape and just know how many lines of symmetry. So if we start with the first one, I can see that if I vertically put a line right here, assume that's straight, that when I fold left to right, it matches. Okay. I also see I could go horizontally. Now, if I look at the horizontal one, then I could maybe interpret or continue to assume that if I go through the other angles, I'd also have symmetry. And so what I mean by that is if you go like this, that will match. Now try to ignore my first line, but if I go to match, this angle here would fold over and land on this one. So I'm also able to go like with that angle. And then back to the vertical line, if I'm going through the middle of a side, it's going to work through the other sides as well. So what we end up getting here are 6 lines we can draw. If we go through each vertex goes through the opposite vertex. So even though there are 6 vertices, there's only 3 lines I can draw through the vertices. And then I can go through the 6 sides, but each side has an opposite side as well. Okay, you might try B and C. Pause here and see if you can come up with B and C. Okay, for part B, since it's not a regular shape, it doesn't have every single angle on every single side. So I am able to go vertically and horizontally, but I can't go diagonally, and let me show you why. Let me erase these. So if I go diagonally like this through a vertex, what's going to happen when I go to fold? So then, like if I were to look on this side of my shape, when I go to fold, this angle here will land up here. And see how it doesn't exist up there. So that is why we can't go that direction. Come on. So I would just have 2. I got my vertical and my horizontal. The last one, you can only do 1. You can just go right over there. So just 1. Okay, try the bottom 3. Go ahead and pause it and try those bottom 3. Okay, on the first one, we're going to have 5. We're going to be able to go here. We're going to be able to go here. So through each point, I don't know why my lines disappear as I draw them. Through there, and I'm going to be able to go through here. Oh my goodness. Okay. All right, I don't know what's going on. I'll try to keep going on the video. All right, so I only have 5. Okay, the butterfly, you can just go 1 right here. So there's just 1. And then the kind of snowflake at the end, it's going to be similar to that the hexagon from before. There's going to be 6. Okay, so you're going to be able to go through each of the 3 vertices, or 6 vertices, which picks up all of them. Then you can go through the kind of snowflake part right here. Okay, so that would contain our 6. Okay, let's move on to rotational symmetry. Oh, goodness. Okay, if this keeps going, I may have to start over, but let's keep going. Okay, we're going to try to ignore that line. Gosh, I'm so sorry. Okay, pretend that line doesn't exist. I don't know why that is right there. All right, rotational symmetry. So what I would do here is first of all, it's regular. So I think of how many times, if I'm going to travel in a complete circle, how many times could I stop and have it look identical? So if I were to visualize this hexagon, if I were to take this angle, and rotate it this far, it would look the same. And if I were to keep going that far, it would look the same. And so if you see here, I'm really stopping at each angle. So if there are 6 angles in a hexagon, and if I go in one complete revolution of 360, and if I divide it into 6 stops, then the answer I get is the degree measure of each stop. So 360 divided by 6 is 60 degrees. So when I describe these, I can say, I can go 60. So if I go another 60, I'm up to 120. And if I go another 60, so if I just keep adding 60, I'm up to 180. And so I don't want to go past 180. I'm going to stop here at 180. So those 3 degree measures would be my description of the rotations that this has. Okay, so how many does it break into evenly? 360 divided by 6. And then if it's a regular shape, then it can go that many times and we just keep accumulating. Okay, on our equilateral triangle, since there are 3 equal angles, because equilateral triangles are also equiangular, it can rotate 3 times along the way and stop until you're back to the beginning. So if I do 360 divided by 3, I get 120. So if I rotate it 120 degrees, it would stop. But if I add another 120, I'm over 180. So I can't go over 180, so I would just backtrack and call it 120. Okay, look at your trapezoid. So because it's not regular, and actually I don't know that trapezoids ever could be regular, but because I have this shorter side up here, I actually have no rotational symmetry. Because envision this shorter side, even if it rotates around halfway and stops, now the shorter side's at the bottom, and it won't look the same. So you actually have to travel in 1 full revolution, and if you have to do that, you don't have rotational symmetry. So we would just call that none. Okay, try those last 3 down there. Okay, we're going to ignore that line there. I don't know what's going on. Okay, so back to our regular octagon. So again, I would start with all the way around is 360. There are 8 angles in an octagon. So 360 divided by 8 is 45. So I can go every 45 degrees. Okay, so 45 degrees would be one of them. If I add 45 to that, I have 90. Add 45 to that, I'm up to 135. Add 45 to that, and I'm up to 180, and I can't go any farther. Okay, so I would say that a regular octagon has those angles of rotation. My right triangle here has none. It has to go all the way around to look the same. So that does not give me any rotational symmetry. My parallelogram does have a rotational symmetry of 180. Okay, it can go halfway around and look the exact same, and then it goes halfway around to be back to the beginning. So we'd call that 180. Okay, that's it for symmetry.